All right, so today we are going to peel back the curtain on one of the coolest processes in all of tech, how an artificial intelligence actually learns. And I promise you, it's not magic. It's a surprisingly elegant journey, and we're going to walk through it step by step.
It really all boils down to this one question. We see AI doing all these incredible things, right? But how does it get there? How does a machine, just a bunch of circuits and code, go from knowing absolutely nothing to being able to spot a cat in a photo, write a poem, or even drive a car? That's the puzzle we're putting together today.
So here's our roadmap for the next few minutes. We'll start with the network as a blank slate. Then we'll figure out how it keeps score of its own progress. After that, we'll follow it on its journey to get better. We'll even uncover its secret compass, learn some pro-level techniques, and finally, see how all this stuff leads to the mind-blowing AI we have today. Okay, let's start at square one. Imagine a brand new artificial neural network, fresh off the digital assembly line. It's not some kind of genius just waiting to be switched on. Nope, it's more like a brain that's been fully assembled but hasn't had a single thought or experience yet. So, you gotta understand, at its heart, a neural network is just, well, it's just pure chaos. It's made of millions of little digital knobs, or what we call parameters, and every single one is set to a completely random value. So yeah, it has the structure to be smart, but its first guess is always going to be a wild one. You show it a picture of a cat, it might say car or apple, and it'll be just as confident about either. It's literally just guessing. Okay, so if our network is just out there making these wild guesses, how in the world do we start to teach it anything? Well, think about it. The first step in teaching anyone, or anything, is giving them feedback. You need a way to say, nope, that guess was terrible. Or, hey, you're getting warmer. You need a scorecard. In machine learning, that scorecard has a name, the loss function. The easiest way to think about it is like a golf score. Its only job is to look at the network's guess, compare it to the right answer, and then spit out a number. If the guess is way, way off, that number is huge. If the guess is dead on, the number is 0. And this is the key, right? The entire goal of training is to get that score, that loss, as low as you possibly can. Let's make this super concrete. On the left, the network sees a cat, but it guesses dog. The loss function sees this, compares dog to cat, and bam, it gives it a high score, a big penalty. But on the right, the network gets it right, predicting cat. And for that, it gets a nice, beautiful low score. This simple feedback loop, this scorecard, it's the engine that drives all learning in these systems. All right, so now the network has its mission. Get the lowest score possible. But how? How does it do that when it's got millions of these random knobs to fiddle with? This is where my favorite analogy comes in. Imagine the network is a mountain climber. They're standing somewhere on a massive, foggy mountain range. Their altitude, that's the loss score. High up is bad. Their goal? Get to the lowest possible point, the very bottom of the deepest valley. Yeah, this quote just nails it. And that fog? The fog is the most important part of this whole idea. The climber can't see the whole map. They can't just look around and say, oh, the bottom of the valley is over there. Nope. All they can do is feel the ground right under their feet and figure out, okay, which way is downhill from right here? And that's exactly what the network does. This whole process is called gradient descent, and it is the absolute workhorse of training. And it's so simple and beautiful when you break it down. 1, you start at a totally random spot on the mountain. That's our network with its random knobs. 2, you check the slope, or the gradient, right where you're standing. That tells you the steepest way down. 3, you take one small step in that downhill direction. And 4, you just do it again, and again, and again. Check the slope, take a step. Check the slope, take a step. Over and over until you can't go downhill anymore. Now, an important question, how big should those steps be? Well, that's controlled by a little setting called the learning rate, and this is so important. If your learning rate is too high, it's like you're taking these giant, clumsy leaps down the mountain. You could jump right over the bottom of the valley and land halfway up the other side. But if it's too small, you're just taking these tiny little shuffles, and it might take forever to get where you're going. Finding that just right learning rate is a huge part of the art of machine learning. Okay, this all sounds pretty straightforward, right? But wait a second, we kind of glossed over the magic part. I mean, it's easy for our climber to feel the slope of the ground. But for a network with millions of knobs, how does it know how to adjust each and every one of them to go downhill? How does it know which way the slope is tilting across millions of dimensions at once? It needs a compass. And that compass has a name, backpropagation.
it's the secret sauce. Here's how it works. After the network gets its bad score, backpropagation goes to work, moving backward from that score through the entire network. Think of it like a chain of command for figuring out who's to blame. It tells every single parameter, hey, you're responsible for this much of the mistake, so you need to turn yourself this way to help fix it. It gives every single knob its own personalized instruction. It's the thing that makes the whole downhill journey possible.
All right, so we've got the basic plan, but just walking downhill isn't always going to cut it. The landscape of these loss functions can be really treacherous. We're talking narrow ravines, weird plateaus, and all sorts of deceptive paths. So to get through it, data scientists have come up with some pro-level climber techniques. So here are two of the biggest headaches. First up, oscillations. This is where a climber gets stuck in a really narrow canyon and just starts bouncing from one wall to the other, back and forth, without actually making much progress down. The other, and this one's much sneakier, is called overfitting. This is like our climber perfectly, and I mean perfectly, memorizing one specific path down one specific mountain. It works great for that one trip, but if you drop them on a new mountain, they're totally lost because they never learned the general rules of climbing, they just memorized a route. To solve those shaky oscillations, we can give our climbers something called momentum. Seriously, think of it like strapping a heavy backpack on them. Once they start moving in a certain direction, they have some inertia. It's harder to change direction on a whim. This momentum helps smooth out their path, so they stop bouncing around, and it lets them just blast right through any little insignificant bumps in the terrain. And this visual, wow, it just shows that tightrope walk perfectly. On the left, that's underfitting. The model is way too simple. It's like trying to draw a curve with a straight ruler. It just misses the whole point. But on the right, that's overfitting. This model is trying way too hard. It wiggles all over the place, just hit every single dot perfectly. It's memorized the random noise, not the actual signal. The sweet spot, the real learning, is finding that perfect balance right in the middle. So, how do we fight that overfitting problem? Well, two really clever techniques are regularization and dropout. Regularization is basically like telling the network, look, I want you to get a low score, but I'm also going to penalize you if your solution is too complicated. It encourages the network to find simpler, more general answers. And dropout is even cooler. During training, it just randomly tells some of the neurons in the network, hey, you, take this round off, just sit out. This forces the other parts of the network to learn more robust patterns so they're not too dependent on any one piece. So why do we care about all these pro techniques? What's the big deal? Well, because mastering this stuff is exactly what allowed us to build much smarter, much deeper networks. It's what let our metaphorical climber reach totally new peaks of performance, and it's what kicked off the whole modern AI revolution. This mastery led to some huge breakthroughs. For instance, a network called ResNet used these clever things called skip connections that finally let us build networks that were hundreds of layers deep without getting lost. Then you had GoogleNet, which, with its Inception module, was all about going wider, analyzing the data in a bunch of different ways at the same time. And DenseNet took things even further, connecting every layer to every other layer for maximum information sharing. These aren't just names on a chart. They're huge milestones built by people who mastered the art of this downhill journey. And that's really the main takeaway here. That abstract process of a climber in the fog finding the bottom of a valley, using a compass and momentum and all these other tricks, that is what powers the real-world AI that recognizes your face, translates languages, and helps doctors read medical scans. So, at the end of the day, when you boil it all down, training a machine isn't some magical black box. It's actually this remarkably logical and, I think, elegant feedback loop. You measure how well you're doing with a loss function, you figure out the best way to get better using backpropagation, and you take one small step in that direction. And then you just repeat that process millions and millions of times. And that leaves us with one last, kind of mind-blowing question to chew on. This process of guided, step-by-step improvement is incredibly powerful. So if this is the basic way that machines learn, by tweaking a complex system to make an error smaller and smaller, what are the actual limits? What's the limit to what they can eventually know? That's definitely something to think about.